Hello everyone. Today we are going to start new chapter, heat exchangers. My first question is, what is heat exchanger? Heat exchanger is a mechanical device used for exchange of heat between the two fluids that are at different temperatures. It involves two fluids, fluid 1 and fluid 2. Fluid 1 is at temperature T1 and fluid 2 is at temperature T2, and they are not at the same temperature. Temperatures are different. There is an exchange of heat, or in other words, we can say it facilitates exchange of some amount of heat. The amount of heat transferred from one fluid to another fluid is directly proportional to the temperature difference. Now, when the fluid flows in the heat exchanger from one point to other point, from entry to exit along the length, there is a change of temperature difference. At the starting, temperature difference is high. At the end, the temperature difference is low. There is a variation of temperature difference. Due to that, we are not going to use the temperature difference method. We will analyze the heat exchanger by using LMTD method, which is also known as log mean temperature difference method. The heat transfer in the heat exchanger, there exists conduction and convection. Conduction, thermal conductivity of the material is important, and it is represented by K. In convection, the heat transfer coefficient H is important. So it is very convenient to work with a new, we can say, overall heat transfer coefficient U. It is very convenient to work with overall heat transfer coefficient U, which accounts for the contribution of all these effects on heat transfer. It accounts for the effect of conduction and convection combined. Throughout the chapter, throughout this presentation, we will cover the topic related to overall heat transfer coefficient, classification of heat exchanger. We will do the log mean temperature difference analysis, and finally we will do the analysis by using the NTU method, which is also known as effectiveness method. Next topic is classification of heat exchanger. Now, heat exchangers are designed in so many sizes, types, and configurations, and flow arrangements. And these are classified according to the heat transfer process. According to that, heat exchangers are of three types. They are direct contact type heat exchanger. They are also known as transfer type heat exchangers or recuperators. And third one under this category is the storage type heat exchanger, or they are also known as regenerators. In direct contact type of heat exchangers, in this type of heat exchanger, two fluids, in this case there are two fluids, and two fluids are immiscible at different temperature, and they come in direct contact with each other. And the example for direct contact type heat exchanger is our cooling tower, or we can say jet condenser. These are the examples. Second is the type which is known as a transfer type heat exchanger. The second is the transfer type heat exchanger. In the transfer type of heat exchanger, the cold and the hot fluid, they flow simultaneously through the device, and the heat is transferred through the wall. In between the two fluids there will be a wall, and heat will transfer through the wall, separating them. These types of heat exchangers are most commonly used in most of all of the engineering. And third one is the storage type heat exchanger. See, under the category of heat transfer process, according to classification according to heat transfer process, next is the storage type heat exchanger. The other name for the storage type heat exchanger is a regenerator. They are also known as regenerators. Now, in these types of heat exchangers, the heat energy is transferred directly from one fluid to another across the solid wall or across the solid surface, which is alternatively in contact with both fluid. What I want to say here that when a hot fluid flows in an interval of time, it gives its heat to the surface, which stores it in the form of we can say an increase in its internal energy. This stored energy is transferred to cold fluid as it flows over the surface in the next interval of time. Uh, the same surface is subjected to periodic heating and cooling. We can say the same surface is subjected to the periodic heating and cooling. These are preheaters, or we can say in for steam power plants, blast furnaces, ठीक है, oxygen producer, etc. Next is the classification of heat exchanger is on the basis of we can say according to the constructional feature. According to the constructional feature, the first one is the tubular heat exchanger. HX is the symbol for heat exchanger. Tubular. These are also called tube-in-tube, concentric tube type, or other name is double pipe heat exchanger. They are known as double pipe heat exchanger. They are also known as tube-in-tube or concentric tube type heat exchangers. These are widely used in many sizes and different flow arrangements. And under this under this category, the next is the shell and tube heat exchanger. Shell and tube heat exchanger, these are also called surface condensers. These are also called surface condensers and are mostly used for heating, cooling. They are also used for condensation and evaporation application. Shell and tube heat exchangers. It consists of shell and a large number of tubes, parallel tubes housing in it. The heat transfer takes place as one of the fluid flows through the tubes and other fluid flows outside the tube through the shell. And the next for under this classification, the next is known as compact heat exchanger. The next is known as compact heat exchanger. Compact heat exchanger. The next one. These are the special class of heat exchanger in which heat transfer surface area per unit volume is very large. As the name indicates, they are compact heat exchanger. The main feature of these type of heat exchanger is heat transfer surface area per unit volume is very large. The next is under the classification of heat exchanger. Next we can classify the heat exchanger according to the flow arrangement. Under this, the first one is the parallel flow heat exchanger. In parallel flow heat exchanger, consider the tube-in-tube heat exchanger, concentric tube type heat exchanger. If the hot fluid is flowing from one direction from left to right, for the case of parallel flow, the cold fluid will also flow along the same direction. It is known as parallel flow heat exchanger. For the counter flow, For the counterflow heat exchanger, let's say it is the inner tube and it is the outer tube. Hot fluid is flowing through the inner tube and cold fluid is flowing through the outer tube, but in opposite direction. If their direction is opposite to each other, then it is known as counterflow. One fluid is flowing along this direction. Suppose it is a hot fluid. The cold fluid is flowing in the opposite direction. Then we can say it is a counterflow heat exchanger. The third type of heat exchanger under this category is a cross flow. Next is the cross flow heat exchanger. In cross flow heat exchanger, the two fluids flow at right angle. Two fluids, suppose one fluid is flowing along this direction, the other fluid will flow at right angle to each other. The cross flow heat exchanger is further classified. They are unmixed. They are unmixed flow, and we can say second one under this category is mixed flow heat exchanger, depending on the flow configuration. If both the fluids flow through individual channels and are not free to move in traverse direction, the arrangement is called unmixed flow. Otherwise, the arrangement is called mixed flow under the category of cross flow heat exchanger. Now let us try to understand the temperature distribution through the heat exchanger. Two important arrangements are parallel flow and counter flow. For parallel flow, I am going to draw the diagram for parallel flow. For parallel flow, let L is the length of the heat exchanger. L is the length of the heat exchanger. We are interested to find the temperature distribution. This is the inlet side and this is the outlet side of the heat exchanger. Fluid will flow from inlet to outlet along the length. Fluid will flow from inlet to outlet along the length. The temperature distribution for cold fluid and hot fluid. Due to exchange of heat, temperature of the cold fluid will rise. Temperature, we are going to assume it is, let's say, inlet for cold fluid inlet, and this is the line for outlet. Cold fluid inlet, let it is TCI. Its temperature will increase from inlet to outlet from TCI to TCO. The temperature of why the temperature of cold fluid is increasing? Because this is in contact, this fluid is in contact with other fluid which is at a high temperature. Its temperature, let's say it is THI, inlet temperature of hot fluid. Due to exchange of heat, hot fluid temperature will decrease along the length. Its temperature will decrease from THI to THO. This is the arrangement for parallel flow heat exchanger, tube in tube parallel flow heat exchanger. If we are interested to draw the temperature distribution for counterflow heat exchanger, it will be like this. This is that L is the length of the heat exchanger. Hot fluid temperature side will be on the upper side. Its temperature line will be like this: THI, hot fluid inlet temperature, hot fluid outlet temperature. Now it is the arrangement for counterflow. This is the arrangement for counterflow heat exchanger. The first, we have done the arrangement for parallel flow heat exchanger. For counterflow heat exchanger, the temperature of the hot fluid will decrease. There will be exchange of heat because at the same time in the opposite direction, this will be the inlet for cold fluid, TCI. The temperature of the cold fluid will increase from TCI to some value TCO. The direction of the fluid will be in the opposite direction. Cold fluid outlet will be temperature here. The next topic is overall heat transfer coefficient. It is represented by symbol capital U. A tubular heat exchanger usually involve two flowing fluids. There are two fluids, fluid 1 and fluid 2. There will be two fluids. They will be separated by a solid wall. In between there will be a wall, and the first heat is first transferred. We know the heat is first transferred from the hot fluid to the wall of convection. We know this. First of all, I am going to show you one diagram. Let's say it is a one diagram with the help of which I am going to explain what I want to say, that it is a diagram for tube in tube concentric tube type heat exchanger. Hot fluid will flow into the inner tube and cold fluid will flow through the space, or we can say annular space available in between these two tubes. The heat is first transferred from the hot fluid to the wall. Heat is first transferred from the hot fluid to the wall by convection. Then heat will transfer through the wall by conduction, and finally the heat will transfer from the wall to the cold fluid by convection again. The total thermal resistance associated with the heat transfer process involves two convection resistances and one conduction resistance. There will be two convection resistances and one conduction resistance. Let us assume a few parameters like area, that AI is the inner area of the inner tube, and assume AO is the outer area of the inner tube. We know pi d inner and length, pi d outer and length, where L is the length of the tube and di and do are the diameters of inlet and outlet of the inner tube. So we can also represent this space, this wall, as an enlarged view. Let us try to understand what is that. This pipe, the wall of the pipe is represented here. This is the inner side. This is the temperature Ti, having temperature Ti, hot fluid having temperature Ti, and heat transfer coefficient Hi. The area, inner area will be Ai, and at the outer side area will be AO. Heat transfer coefficient HO. Heat will transfer from the hot fluid to the cold fluid through the wall, and we can also represent this whole system via electrical network method. We can draw three resistances: resistance for convection, resistance for wall, and resistance for outer convection. We also know that heat transfer can be represented. We also know that heat transfer can be represented as total thermal potential divided by total thermal resistance. We know this. We will apply this equation again and again to find the resistance for the convection resistance, for wall resistance, and finally the convection resistance at outer side, and again finally for the total resistance also, for the total heat transfer also. We know there are three resistances. First one is the wall resistance. Wall resistance can be calculated by conduction. Fourier law of heat conduction, the formula is like this. And the thermal resistance, which is the summation of all resistances, it is also known as total resistance. It consists of three resistances: convection inner side, convection outer side. In between there is a wall resistance. We can find the equation for total resistance by putting the value. It is the convection resistance inner side, convection resistance outer side. These are the convection resistance inner side, convection resistance outer side. In between there is a wall resistance. Q can also be written into the form of delta T divided by resistance, the total potential divided by thermal resistance. And we can also represent this equation into the form of overall heat transfer coefficient UA delta T. And if we consider this equation corresponding to the inner area, equation will be in the form of UI AI delta T. Otherwise, it is also equal to UO AO delta T, which is the equation on the basis of outer area. Now, if the total thermal resistance, it can be represented by 1 over UA, because UA is the conduction, the reciprocal of it will be a resistance in the form of inner UA and inner area. This is also equal to 1 by U on the basis of outer area, and UO on the basis of outer area, and AO is the outer area. Now the UI will be, from this equation we can find the UI will be by rearranging the equations. UI will be 1 upon summation Ri thermal divided by AI, and when we will put the value of resistance in this equation, the final equation will be like this: 1 upon divided by 1 by Hi AI divided by pi KL 2 pi KL log of DO DI plus AI upon AO HO. After arrangement, this equation can be easily obtained. After rearrangement, this equation will become this. This equation will take the form of this, and then the same things, same procedure, same steps can be followed for U outer. We have done for the overall heat transfer coefficient for on the basis of inner area. Now we can find the overall heat transfer coefficient for outer area. Same steps, all steps are same. We will follow the equation like this. After rearrangement, the final U will be this, which is on the basis of outer area. The final U will be this on the basis of outer area. If you know when the wall thickness of the tube is small, when the wall thickness of the tube is small, in that case its thermal conductivity is high, and its thermal conductivity is high, thermal resistance of the tube material will be neglected. Then we can neglect the R wall, which will be equal to 0, and then the inner and outer surface of the tube are identical. For that case, we will took AI will be equal to AO, and your equation will take the form of U is equal to 1 by divided by this quantity 1 by Hi plus 1 by Ho, where Hi is the heat transfer coefficient on inner side, Ho is the heat transfer coefficient on outer side. The overall heat transfer coefficient U is dominated by the smaller heat transfer coefficient, since the inverse of the small value is large. If one of the convection coefficient is much smaller out of these two, if one of coefficient is much smaller than the other, the value of the overall heat transfer coefficient is almost equal to the smaller convection coefficient. We can say u will become, for that case, u will become h smaller. Out of these two, the value of which is smaller, you will take the value of that, h, u will be equal to h smaller.